All right, hello everybody. This is going to be section 3 of chapter 10. We're going to talk about solids, and in this particular section, we're going to cover the different properties of our solids related back to kinetic molecular theory, which is, of course, a daily question I asked you last week. We're also going to talk a little bit about the properties of solids. Some you already know, some we're just going to go in a little bit more depth. And then we're going to end with binding forces in solids and crystals specifically. And we're going to talk about crystalline structure versus amorphous solids, which is something you're probably not quite familiar with yet. All right, so in order to start us off, and remember that you can always pause these videos and you can go back and you can look at things. Use that to your advantage. You have the ability to do that with your computer. That's the beauty of one of these, is that I can go pretty fast, and you can always go back and review this as many times as you like. So some of the things we know about solids: particles are going to be more packed, particles aren't going to move as fast, they're going to have stronger interactions between each other, so between particles, aka stronger intermolecular forces, which is something we've been covering in this chapter as kind of like a background topic. Those attractive forces are the ones that are actually responsible for the particles of a solid not moving very fast. Now, solids are usually considered more highly ordered than liquids for a lot of reasons, but one is because our particles in a solid cannot slide past each other, whereas in a liquid they very much can. Okay, and then that brings us to our first lecture question. So what are the properties of solids according to kinetic molecular theory? And this is a topic covered in our books. This is a topic covered in our lecture. We just talked about what makes them very similar, and what actually controls solid particles according to kinetic molecular theory. So go back and look at that previous slide if you need to. Go back and look at your book if you need to help you answer this question. Pause and answer the question. You're going to turn this in via email. So answer this question, and then when you're ready, you can go ahead and you can move on. So I'm going to keep going because I don't need to answer the question because I already know the answer. And we're going to talk about the two different kinds of solids that are covered in this chapter: the crystalline solids and the amorphous solids. Our crystalline solids are going to be what we consider highly ordered. They have geometric shapes, so they are face-centered or cubic and things of that nature, and we'll talk about those a little bit here in a second. And then we're going to talk about amorphous solids, where our particles kind of act randomly. They're not in a highly ordered crystalline structure, and we'll talk about why that might happen as well. Okay, so something to remember about our solids: one of the properties, definite shape, definite volume. You put a solid in a container, it's not going to actually take the shape of the container like a liquid would, and it's not going to fill the whole container like a gas would. And we know this to be true because we can see this with our own eyes. They're pretty much, whenever you have a solid cut into a specific shape, a lot of times that solid stays in that shape. This is especially true of crystalline solids. Now, amorphous solids have the ability to kind of change shape over time. Think when they are under certain pressures or certain temperatures. Now, the volume of a solid is only going to change like a very tiny bit if we change our temperature or pressure. And that's because, again, definite volume. But what happens when you heat up anything? It moves faster, right? So our particles can start moving faster. And when we say the volume changes only slightly, if we start heating a solid before it starts to melt, we're going to see that the particles do actually change, and the volume of those particles does change as well, very slightly, but still. A lot of times what this also does is it affects how they're packed, in that it may move certain particles that are at the edges of our solid away. That's that whole melting process. Or if it goes directly to a gas, it may sublime, so those particles may escape complete order altogether. The next thing to talk about is a definite melting point. So there is a definite temperature at which our physical change of a solid happens. It'll either become a liquid or a gas, depending on the pressure. That was one of those phase diagrams we looked at in a previous session. And what we're going to see is that when our solid becomes a liquid, we call that phase change is called melting. Now, our next section on section 4 is going to cover those phase changes in depth, and we'll see what are the names of those phase changes here in a second. But for now, what we need to know is just that change from solid to liquid is going to be considered melting. And what actually happens is we're heating those particles up, they're moving faster, the kinetic energies are increasing of the particles that are in the solid phase, and when they increase, they start to move a little faster. They kind of vibrate in place for a little bit, and then they start to kind of flow, and that's that melting process. And we'll talk about phase changes a lot in the next section, but when we say this is the melting point of a solid, it does not mean that instantaneously everything melts. That is not what happens. In fact, it takes quite a long time for that to occur in some different phases, and we'll talk about that flat part of a curve here in a minute. Okay, another thing to understand is that amorphous solids are not the same. So things like glass and polymers like plastics do not have a single melting point. In fact, some parts of those different materials may melt at one temperature and some parts may melt at a different temperature. A lot of times this has to do with the composition of what it is. So we see an uneven distribution of particles. So in one part it may be very packed with silicon particles, like say for a glass, for example. We may see a definite section of particles that start to melt a little bit earlier than other sections might be. And this is because these substances are not what we call evenly distributed. There is no specific format for an amorphous solid. Sometimes we call them supercooled liquids. So when they go from a high temperature to a low temperature very quickly, that would be the term supercooled. And a lot of times what happens is they retain the properties of the previous phase they were in before they were cooled in the first place. All right, here's your second question. I'm going to give you a second to answer. And there are properties of an amorphous solid that make it like a liquid. There are also properties that make it like a solid. I want you to name them. Give you a second. And I'm going to move on. Again, you can pause. All right, next thing is the property of solids to be dense and incompressible. So again, think of the strongest solid you can think of, maybe like a rock. I have a rock on my desk, so I'm kind of looking at it. If you try to push on that with all the force you possibly can, eventually, yeah, you might break it, but you're not going to compress it. You're just going to change its shape. Another thing is solids are very well known as being highly dense because our particles are packed as close together as they possibly can be. And you saw this in your simulation that you did last week with the solids, liquids, and gases. If you examined the solid phase closely, a lot of solids, when they are in the solid phase, are very densely packed together. The exception to that is water, and we've talked about why water is weird, but this is another reason why water is weird. When water is in a solid form, its particles kind of spread further apart than they do when they are in the liquid form. So that is just like an odd property of that specific substance. It's one of the reasons why we think there's life underneath a lot of the ice up in the Arctic, because our particles are further apart, which means they're allowing air to get through, which also allows life to exist, even in weird temperatures, weird pressures, etc. But for our specific, off the water tangent, for our specific descriptions of solids, we're going to say that they are incompressible and that they are more dense in the solid state than they are in the liquid or the solid or the gas phase. Another thing is the low rate of diffusion. Diffusion, remember, means how fast something mixes. Solids are going to take the longest to mix into other solutions, whether those solutions be other liquids or gases or other solids. You put two solids next to each other, they're not going to do a whole lot. They're just going to stay solids. You toss a solid in water, it's going to take the longest to diffuse through that water, but it will diffuse. We call that process, not diffusion, dissolving a lot of times. Okay, next thing is going to be on crystals. And so crystalline solids, a little different than our amorphous solids, moving into crystal structures, very, very ordered solids. Okay, and what happens is when we look at the particle level, we're going to see what we call a lattice. That lattice is going to have even distributions of particles in a very specific arrangement. And we call that arrangement a unit cell. And we're going to look at the three different kinds of unit cells here in a second. But those unit cells are really just the basic three-dimensional pattern of the crystal lattice itself. So we take a crystal structure and we break it down into what we call a lattice. The lattice is like the highly ordered GPS coordinate system, if you will. And then we look at that GPS coordinate system and we break it into one of three possibilities referred to as unit cells. So there are three. The first is simple cubic, exactly what you think would happen on the far left there. When you put rows of round objects on top of each other, you would think they would either look like this simple cubic or something along the lines of a body-centered cubic. So if you extend that body-centered cubic unit cell out and you had more particles around where you see the center layer is, that is one of the two ways you could overlap two are 3 layers of particles. And so when we think about unit cells, obviously we're looking at just like a small subset, but if you extend these infinitely in every direction, that's the actual unit cell, right? So that's what the actual crystal structure is going to look like. For us, we break it into one little part and we call it a unit cell. So we've got the very simple cubic. We've got the body-centered cubic, which kind of overlaps them offset. And then we've got the face-centered cubic, which overlaps them offset and fills in every possible space when it comes to using spheres. So the face-centered cubic is one that's actually pretty common as well. All right, so that being said, we have binding forces to talk about. So we're going to talk about the crystal and the unit cells in general. They have there are 7 different kinds of symmetry. Those 7 types of symmetry are listed in your book. You do not need to memorize them, but do know that there are 7 of them, and do understand that each one has a different kind of shape to bring to the table. So if you look them over, they're on page 327. There are 7 of them in general, and there are some really cool examples of what the different crystals look like as far as their symmetry is concerned. And how we get these types of symmetry involves the binding forces. And so this is how particles actually bind together into the crystal structure that we're talking about. And we're talking about things like the intermolecular forces, but we're also talking about chemical bonding in between particles. So we've kind of moved away from just how does one molecule bump up against another molecule, also known as an intermolecular force, and we're moving towards how do they actually bind together? Because in order for them to stay together, there's got to be a stronger force than just the one that's holding them next to each other. There's got to be something that's actually binding them together, because if you've ever tried to break a crystal of any kind, it's very difficult to do once it gets down to a certain size. And so one of the things to note is we have these different types of particles. We've talked about all of these before except for that covalent network in the middle, and that's the crystalline structure that we're really going to focus on today, is that covalent network. We've got ionic compounds, which we've talked about before, typically have pretty high-ish boiling points. The things that typically don't have very high boiling and melting points are the nonpolar and polar substances that we've mostly focused on in previous chapters. So ionic, metallic, covalent network substances are all going to have pretty high boiling points, pretty high melting points. It makes sense if you think about this. SiO2 is glass. We would not want that melting at the temperature that we live at, aka 25 degrees Celsius most days. We would not want diamonds melting at our specific room temperature. So these melting and boiling points make a lot of sense. And the highly ordered nature of the solids is what keeps them from melting. Okay, that brings us to our first force, which is going to be ionic crystal structures. So this is the ionic crystals that are going to form between group 1 and 2 metals and group 16 or 17 nonmetals, aka sodium chloride, group 1, group 17 halogen. And those two things are going to have what we call an ionic bond. That ionic bond is basically made of the positive being attracted to the negative, the positive sodium atom being attracted to the negative chlorine atom, and when they are attracted that way, they kind of order themselves in a regular pattern. And this is a very good example of one of those 3 different unit cells. Now, these ones are going to be pretty easy to break into smaller and smaller pieces, aka they are brittle, but they're also very hard and they're very good insulators. Again, high melting points. Good for a lot of reasons. One is we don't want our salt melting at room temperature. We actually want it to melt much, much lower than that for a lot of reasons. All right, that brings us into covalent network crystals. That's going to be just a way of putting our atoms covalently bonded to the nearest atom it is. So this is the glass. This is the carbon common structures of carbon, things like buckyballs and diamonds. Those are gonna have this specific type of bonding. Again, very hard and brittle, very high melting points, usually non-conductors or semiconductors, good at kind of doing stuff. All right, very stable, kind of useful as far as electricity is concerned or heat is concerned. Covalent network crystals are not usually there to do things of that nature. In other words, if you want to heat your home, you're not going to insulate your entire house with glass. You're going to insulate your entire house with insulation for a reason. And we'll talk a little bit more about types of solids that are actually better at conducting or, preserving heat, things like that. Our next one's going to be metallic type crystals. So think of a metal, any metal, and this is how, say, a chunk of iron is found out in our environment. Now, one of the coolest things about metals is that they are surrounded by electrons, and not just electrons, but delocalized electrons. So delocalized, of course, means electrons that are not bound to the atom itself. Those electrons are going to actually come from the metal atoms, and those electrons, when they leave an open space for new electrons to come in. This is what makes them very good conductors. We're talking about, we use copper wire to transmit our electricity for a lot of reasons, but one of them is that it leaves one electron open when one leaves, right? It leaves like an empty space for an electron to kind of come across. And electricity is the flow of electrons. So in order for electrons to flow, they have to have spaces to go. So we just kind of create these openings where electrons jump from place to place to place. And in jumping, they're transmitting those electrons from one place to another. So this is where we get that conductivity of our metals. And think of the most conductive metals that you can, and that this is the property that makes them conductive. Our next one and our last one is going to be the covalent molecular crystal binding forces. This is just going to be, if you look back to our second one, these guys are going to involve molecular compounds instead of just actual, these are going to involve molecular compounds versus covalent compounds. Remember, the term molecular means organic or carbon, hydrogen, oxygen. So these are just made of non-metals. And these are only going to be held together by, these are going to be mostly held together by intermolecular forces. So these are going to be covalently bonded molecules that are then connected to the next molecule by an intermolecular force, like the London dispersion force. So for instance, if you think of like carbon dioxide, 2 molecules of carbon dioxide. Within the carbon dioxide molecule, you have the C connected to each oxygen using a covalent bond, so sharing 2 electrons. And between each of the carbon dioxide molecules, you have an intermolecular force, like the London dispersion force, that actually holds it together. So this is the more common way that we think of some of our liquids actually interacting, but this happens with covalently molecular bonded substance as well. Okay. All right. From there, these are just, just one last thing to note about these covalent molecular crystals. They have pretty low melting points. They're easy to become gases. They're good insulators. These are the things that we want to use to insulate heat because they're not going to allow a lot through, but for the most part, they are very good at being manipulated, aka they're soft. Okay. Amorphous solids, just to kind of remind you, they don't have a pattern. They have a lot of good properties, but these are not the types of solids we would use to, say, insulate our homes. They have unpredictable shapes. They're not very stable. If you've ever tried to heat glass before, glass heats up A, very quickly, and B, is very easy to break because it is an amorphous solid that has been converted to its shape when it was in a liquid state. It was pretty much super cooled. And if you've ever watched glass blowing, what they're doing is manipulating that amorphous solid into a shape of their choice, and then they're going to let it cool really, really slowly, because if they don't, it breaks very quickly. So just kind of keep in mind, if you think of an amorphous solid, you're trying to come up with an example, think of something that if it had a rapid change in temperature and it would break or change shape, that would probably qualify as an amorphous solid. So ceramics can break pretty easily, sometimes under those conditions. Yeah. A lot of your plastics are amorphous solids of some kind. They kind of, sometimes they'll melt, but they don't melt in a reliable way, things like that. With that is the end of lecture for section 3, and this is your last question. So go ahead and pause it, answer your last question, and email me these questions under the heading of 10.3. Thanks. We'll come back to section 4.